Hello BC class, this is Mrs. Lee, and we're going to try a video lecture today, period. I'm going to give you these notes, and so if you would just listen and follow along as I'll go through the lecture today, and then I'm going to hand out the notes for you to read again later with a little more detail, okay? Today our subject is Taylor polynomials. And a Taylor polynomial is a very specific type of polynomial, and a Taylor polynomial is a power series. I think I mentioned power series last time in class, maybe just briefly, but a power series is a polynomial with an infinite number of terms. And so a Taylor polynomial is a power series. And what we're going to do with our Taylor polynomial, and what the purpose of the Taylor polynomial is, it is to model functions at a specific chosen x value. Now you're asked, well, why do we want to do that? I'm going to give you a brief answer here, and then we can look in more detail when I'm back in class at how a Taylor polynomial reduces the amount of error associated with the model, and it's also much easier to integrate a polynomial than it is to integrate, say, some complicated function. And so that's how it was originally developed. Let's just say the two guys that developed it, Brooke Taylor and Gregory McLaurin, they were able to integrate simple functions, e to the x dx. That was easy. But the question came, how do you integrate something like e to the x squared dx? And so they developed a Taylor polynomial which could model the simple function and then use some substitution techniques to substitute in an x squared versus an x, and they could develop a polynomial that models the e to the x squared. And so that's how it was originally developed, and it may have some practical applications in programming and things like that, if you're trying to model, again, another function. But let's look at some other specifics. All right, so let's start out by developing a model for a polynomial. Let's say it's going to be of fourth degree, and that polynomial is going to approximate e to the x. And if we do that, let's just put some constants in here first. Let's say there's a constant. We need to check for that. Then the next term might be a sub 1, x to the 1. There could be a term in the first degree. There could also be a term in the second degree. As many terms as we want to look for. And dot, 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 x to the n, and oops, a to the n would be out in front of that. Okay, specifically, we're going to look at a way to find these coefficients, a sub 0, a sub 1, a sub 2, in a way that reduces the error and creates a good model for our function. Okay, so there's a formula that we're going to use for each term of our polynomial. Let me just write the formula here, and then I'll explain each part of it in just a second. So, okay, this is the formula for each term. All right, so n, this is an n right here, n is the degree of the term. Okay, C is where the polynomial, and I'm just going to say Pn of x, is centered. That way I don't have to keep writing the word polynomial. Alright, so we can choose it to be centered at 0, and if that's the case, then this is just x to the n. But if we choose for it to be centered at 1 or 2, then it's a horizontal shift to the right of 2. If it was centered at -2, then we would have an x plus 2 here instead of an x minus c. Alright, over here, what this means is this is the nth derivative of the function we're modeling. Oops, our modeling. So we're going to take derivatives and we're going to use them in that term, and then the n just represents the degree to the factorial. So the actual coefficient is going to include, let me get a different color marker here so I can highlight it, the actual A1, A2, A3, A4, this particular part of the formula, the Taylor formula, is going to be the coefficient. And we'll use that later to determine some things. So our Taylor polynomial for our function e to the x is going to look something like this. F of c is going to be the first term plus f, the first derivative evaluated at c, times x minus c, plus the second derivative, and you can put a 2 up there or a little hash mark, c over 2 factorial. This is over 1 factorial, and this is over 0 factorial. Then this is actually x minus c to the 0. I could stick that in here because the first term, and this is the 0th derivative over 0 factorial, if we're going to follow the formula. And let's go back over here, x minus c squared, so that's the second degree term. And then let's just go ahead and write the third degree term, evaluated at c, and then x minus c cubed over 3 factorial. And we could continue to add terms, and every time we add a term, we're going to continue to reduce the error, or we're going to continue to improve the model as we add more terms. Alright, so your instructions may say find a third degree polynomial for the function e to the x about, and let's do x equals 0. Or actually, let me back that up. And let's just say it's going to be about c equals 0. So when c equals 0, this is a Maclaurin polynomial. If c is not 0, we'll just go ahead and add these to the note. It's called a Taylor polynomial. Okay, since we're running out of room on this little page, we're going to use this formula, and I'm going to go to the next page, and then we're going to fill it in. Okay, so now we have a new page, and what I did here was I rewrote what we had before, except where I had x minus c, since c was 0, this term, then I'll just try to circle it here. Instead of x minus c to the n, it's now just x. And I went ahead and rewrote this first term as the 0th derivative, and then x to the 0 power over 0 factorial. So if it's the 0th derivative, let's just go back, and what we're going to find here is that this is actually going to just be f of c, because we're not going to take any derivatives. Okay, so to come up with your Taylor polynomial, the first thing you need to do is take your derivatives. And then the second thing you're going to do is evaluate them at c. So our f of x, or p of x, f of x is going to actually be e to the x. F prime of x is going to be e to the x. This one's easy, that's why I chose this one. F double prime of x equals e to the x. And then f, I'm going to use the little hash marks here, f triple prime of x equals e to the x. Now let's come over here and evaluate it. We're going to have f of 0. That's going to be our first term. That's going to be e to the 0, so that's going to be 1. And then f prime of 0, well, guess what? They're all going to equal 1. So that makes, again, it easy. Now, that's not always going to be true, but we'll do one here in a minute. So now that we have our derivatives and we have evaluated them at c, remember, this right here is c, so we are ready to substitute into our formula up here. So e to the x, and we're ready to come up with our third degree polynomial, is going to be, our first term is simply 1 times x to the 0, which is 1, over 0 factorial, which is 1. Then plus our second derivative, and I'm looking right up here now, is going to be evaluated. C is also 1 times x to the 1 over 1 factorial, so we'll just leave that alone. We don't need to put a 1 maybe in the denominator. And then here we are with our third term, so now I'm right here, and the second derivative is 1 times x squared over 2 factorial. I'll leave the 2 factorial there, and then let me see if I can sneak in this last term. Again, it's 1 x cubed over 3 factorial. Alright, so now let's simplify that as much as we can, and we're going to have e to the x equals 1 plus x squared over 2 plus x cubed over 6. So there is our third degree polynomial, Maclaurin polynomial. I'm just going to abbreviate there, P3 of x, and it's approximating our function e to the x. Okay, so let's do a little exercise with your calculator now, and if you would just, I'll tell you to pause the tape and give you time to enter what I'm telling you to enter into your calculator to show how after each term the polynomial more closely models the function. So let's start out, if you would, by putting in your y1. Let's put e to the x. I want you to set your window to, and let's do x min equal -3, x max equal 3, and then y min, let's see, equals -0.3, and y max equals 4. Alright, I'm going to just tell you to pause right here and do that. Alright, so now I want you to enter into your y2 the first two terms, 1 plus x, of our third degree Taylor polynomial. And I want you to graph these two functions together. I want you to compare what they look like and how close this function is to this function, again, about x equals 0. So just look at that. Alright, so what you just graphed probably looks like the tangent line at x equals 0. And it's exact right at x equals 0, but as it gets further and further away, it doesn't exactly approximate the function. So this is our function. Alright, so let's keep going. And now what I want you to do is put in this into your y3 and this into your y4. And you can use vars, y vars. You could say y2 plus x squared over 2. And you're adding the next term in our polynomial. And then for y4, you can say y3, use vars, y vars, plus x to the third over 6. All right, now I want you to graph those, and if you'll have your calculator graph them in sequential order, what you should see is that as you add these higher degree terms, then the function more closely models or hugs the original function e to the x. All right, I'm going to stop and y'all can do that and you can talk about it. And I'll show you next my picture from my calculator. Okay, so the blue line is e to the x. And then here's the first two terms. That's the 1 plus x. That's the tangent line. And then it gets a little fuzzier, but this is the second degree, 1 plus x squared over 2. So it is a parabola. And as you can see, it's starting to hug this blue line even closer. And then this purple, if you can see it down here, again, it hugs it even closer. And that is the 1 plus x squared over 2 plus x cubed over 3. And if we kept adding terms, again, around x equals 0, it would continue to hug that e to the x line even closer. Okay, so let's do another example, and this is going to be something like you'll have in your homework. So let's just say this is example 1, and your homework's going to say something like find a Maclaurin polynomial of degree n equals 6, and it's going to say for let's just say cosine x equal f of x. See if I can make that look a little better. About c equals 0. So the first thing you want to do is you want to find your derivatives. And so f of x is going to be cosine x. We know that. F prime of x is going to be negative sine x. F double prime of x is going to equal negative cosine x. F triple prime of x is going to equal sine x. And we're going to start repeating. That's a triple. And then we're going to keep going. So we're going to say f, I'm just going to write a 4 now. The fourth derivative of x is, of sine x is cosine x is cosine x. And I'm going to keep going down the page here. Since we're doing a 6th degree, I'm going to have to find 6 derivatives. So the 5th derivative, again, is negative sine x. And then the 6th derivative is going to be negative cosine x. All right, then you're going to go down and evaluate, since the center is 0, you're going to evaluate each one of these to help you find your coefficients and your constants. F of 0, so the cosine of 0 is 1. And okay, so here are all your derivatives. And now you're ready to write that 6th degree Taylor polynomial. All right, let's go ahead and write up here the formula for each of those terms again. So the coefficient, well, each term is going to be f, the nth derivative evaluated at c, times x minus c to the nth derivative all over n factorial. All right, so cosine x is approximately, now our first term is always just going to be the function itself evaluated at C. So in this case, that's going to be 1. Now, the next term we're going to say plus, and then it's going to be the first derivative, which is 0, times x to the 1 over 1 factorial. And I'm going to have to kind of wrap this around here. But then the next term is going to be negative 1, so it's the second derivative times x squared over 2 factorial, and then plus, and then our third derivative times x cubed over 3 factorial, plus our fourth derivative, which is 1, times x to the fourth over 4 factorial, plus our fifth derivative, which is 0, times x to the fifth over 5 factorial, and we'll sneak in plus, last one, negative 1, x to the sixth over 6 factorial. Now, let's go back and simplify that. Alright, so you can see here I've simplified that above, and this is our Taylor polynomial of 6 degree, which approximates a function cosine x. Now, you may also be asked to calculate the error of that polynomial. So let's say you're asked to do that as part of your homework. And the question might be, use P, that 6 degree polynomial that you found, P6 of x, to approximate cosine of 0.1. Oops, I can't get my pen to write there, sorry. Here we go. All right, so what you want to do is then just plug 0.1, excuse me, into your Taylor polynomial. And then come up with an answer. So 0.1 fourth over 4 factorial, and then minus 0.1 to the 6th over 6 factorial. And if you calculate that, you're going to get that that's approximately 0.995. All right, and if you want to go ahead and then find cosine of 0.1 on your calculator, which I know seems a lot easier, then you can compare the two and see what the error is. Okay, so when I put it in my calculator, gosh, it's pretty close. With that 6 degree Taylor polynomial, we just estimated cosine of 0.1. It's important that 0.1 is close to 0, so that makes our approximation even more accurate. The other thing I wanted to point out about the cosine function is that if you notice, each term is even. And remember, cosine's an even function, so that's how you can remember this is a polynomial that you will have to memorize this particular function as a Taylor polynomial when you go into the AP Calculus test. All right, let's do one more type of example, or maybe two, off of your worksheet. All right, let's do number 8 on your worksheet 13.1. So if you want to pull that out. All right. Now, sometimes we're given the function and we're asked to find the polynomial. That was what happened up here. But then sometimes we're given the polynomial and we are asked to find the derivatives of the function. And that's what's happening in number 8. So we are told that we have P6 of x equals 3x minus 4x cubed plus 5x to the 6th. And in A, we are asked to find f of 0. Well, here's what you know. There is no constant in this polynomial, so you know that f of 0 has to equal 0. because of the formula that we used for each coefficient. And if we know that this is x to the 0 over 0 factorial times the 0th derivative, then the only thing in this that can be 0 is going to be that constant, which is really just f of c. So f of 0 is 0. And all right, let's look at, whoops, let me move this up. All right, let's do B. And B, it says find f prime of 0. Well, you know that f prime of 0 times x to the 1 over 1 factorial is going to equal 3, because that's the coefficient, is going to equal 3x, sorry. That's the first term. This is the first term, and you just set it equal to the first term. All right, so your x's are going to cancel out, and then if we solve for f prime of 0, that's going to equal 3. All right, now let's look at, let me move this up. Let's do C. All right, it asks you to find f triple prime of 0. All right, so we do have a third degree term, and it equals 4x cubed. So we can say 4x cubed equals f triple prime of 0. We said it's about c equals 0, x to the third over 3 factorial. All right, so our x to the thirds cancel out, and so we're going to have 4 times 3 factorial equals f triple prime of 0, and 3 times 2 is 6 times 4, so 24 equals that third derivative. All right, and I'll let you guys do the rest of those. All right, now if you'll turn, let's do number 12 on your worksheet. Okay, so it asks you, it gives you the first two terms of the Taylor polynomial for sine x. All right, so this is what's given, and it asks you, gives you this Taylor polynomial, the first two terms, and it asks you to use that to help prove this is true. Well, we can divide by x in order to get something that looks like sine x over x. So let's just take this Taylor polynomial and let's divide every term by x. All right, and when we do that, we get 1 minus x squared over 3 factorial. All right, so now let's take the limit of both sides. Limit as x approaches 0 of sine x over x equals the limit as x approaches 0 of 1 minus x squared over 3 factorial. Well, this term is going to go to 0, so then that answer is going to be 1, which this is all a familiar function, but this is a way to prove, once you construct that Taylor polynomial, it's another way to prove that the limit of sine x over x as x approaches 0 is 1. But use the ability to do algebra to both sides, the original function and to the Taylor polynomial, to help you solve the rest of the problems in your homework. And good luck, and I will see you guys next week.